Welcome to the 25th lecture on digital simulation. This is a continuation to the previous video. In the previous video, we have seen how to write circuit files in SPICE. So in this video, we will see two new commands, .model and .subcircuit. So let us consider this example. This is a half-wave rectifier circuit, and we can try to write the circuit file for this example. So here you can see this node can be numbered as 1, this is node number 2, and this is our reference node 0. So the first line is a command line, so star half wave, so it is a command line. Then in the second line we can write Vi is between 1 and 0, voltage source Vi is connected between node 1 and node 0, and it is a sine wave source. Initial DC value is 0, amplitude is 10 volt, frequency is 50 Hz. Then there is a resistance R1 between node 2 and node 0, and its value is say 10 kilo ohm. So that is written here. Then there is a diode connected between node 1 and node 2. So D1, diode name should start with the letter D. D1 is between 1 and 2, and we have to give a name to the diode model. So I am using a name my diode for the diode model. So between node 1 and node 2 there is a diode with the model name my diode. Now we have to define this diode model using .model command. So the syntax is .model, then the name that you have given in the previous line, that is my diode, then simply write D. So this D stands for default diode model in SPICE. This will be a default model, or otherwise you can specify a particular diode model. That also I will show in the next example. Then these 4 lines will complete the circuit description. Then we can write the .trand command for doing the transient simulation for 40 milliseconds. Then .end. So let us try this in LT SPICE. So I have already typed these commands in example 10. So let me open that. So you can write the commands in a notepad file and save it with the .car extension. So you can select file type as all files and save it as .car file, and then you can open it in LT SPICE like this. So I have in the first line is a command line, you can write any command. Then Vi is between 1 and 0, sine of 0 DC offset. Instead of 8 I can give 10. Amplitude is 10 volt. Then frequency is 50 Hz. Let us check whether it was amplitude was 8 or 10. So amplitude we can give it as 10. Frequency is 50. Then R1 is 10 kilo ohm. D1 is defined like this. Let us save and run. So if you run the file, you will get a window like this where you can plot the graphs. Right click and click on add traces. Select V1. So V1 is the node 1 voltage, that is the source voltage. So you can see a sinusoidal source voltage with the peak value of 10 volt and time period 50 Hz. Frequency 50 Hz. Okay. Now let us plot the output voltage also. Add traces V of 2. Click OK. So you can see the output half wave rectified waveform. Since we are using a practical diode model, there will be some on-state voltage drop in the diode. That is why the output voltage peak is slightly lower compared to the input voltage peak. Okay, this is how you can use a .model command in LT SPICE. Now let us check how we can change this diode to a another model. So in example 12 I have already written that. In example 12 I have used 1 and 4001 diode. So the same example with the diode model replaced by 1 and 4001 diode model. So D1 is between 1 and 2, and then previously we have given my diode as a name or label. Here I am using D1 and 4001. Then this D1 and 4001 has to be defined. So dot model name D1 and 4001. Then the parameters are listed after the letter D. Okay, so these are the reverse saturation current and the related parameters of the diode model. Then you can use dot transient command, dot transient 40 millisecond. You can simply write 40 millisecond for simulating till 40 millisecond. If you specify 0.5 millisecond and 40 millisecond, then 0.5 millisecond will be the plotting interval or printing interval between successive points. Okay, let us run this and see. So let us plot both the V1 and V2. So you can see the result. Here I have used a peak value of 8 volt, that is why this input voltage peak is 8 and the output voltage peak is slightly less due to the on-state voltage drop of the diode. So you can use any diode model here. Now coming to the next example. Here in the next example we will see how to use a sub-circuit model. So suppose we have to simulate an operational amplifier circuit like this. This is an inverting amplifier circuit. So we can define a sub-circuit model for this op-amp. So I have numbered the nodes like this: node 1, 2, 3 and 0. The values are given. 5 kilo ohm is this resistance. Feedback resistance is 50 kilo ohm. This Vg will be a sine wave with amplitude 1 volt and frequency 1 kilohertz. Okay, using the equivalent circuit of an op-amp, we can develop a sub-circuit model. So let us see how to do that. So the terminals of the op-amp are non-inverting terminal, inverting terminal and output terminal. So this is the equivalent circuit model. This is the very basic model of op-amp. Between non-inverting and inverting terminal, we have a very high input impedance of the op-amp, typically 1 mega ohm. Ri is 1 mega ohm. So this is the model of input side, and the output side can be modeled as a dependent voltage source with the value A times input voltage. Vi is the input voltage. So A times Vi. A will be a very large gain, say 1 into 10 raised to 5. Then there is a series resistance which corresponds to the output impedance of the op-amp, typically 50 ohm. So we have nodes non-inverting INV. Then there is an internal node INT here. Then there is an output node and a common node. 5 nodes are there in the subcircuit. So the subcircuit model can be written like this. The first line in the subcircuit model will be dot subcircuit. Then name, you can give any name to the sub-circuit model. I am using op-amp as a model name. Then we have to list the nodes which will appear in the external circuit. This internal node will not appear in the external circuit. So we need to specify only these 4 nodes: non-inverting, non-INV, common and output are the 4 nodes that will get connected to the external circuit. Okay, this can be specified in any order. Then Ri is between non-inverting terminal and inverting terminal and its value is 1 mega ohm. Then this Ro is between internal node and output node and its value is 50 ohm. Then this dependent voltage source, a voltage controlled voltage source is represented by letter E, Ex. It should start with the alphabet E. The name of a voltage controlled voltage source should start with the E. And so the name given is Ex. Then the terminals of Ex are internal INT and common. So those 2 terminals are listed first. Then the controlling quantity for this dependent voltage source is Vi. Vi is what is controlling this voltage source, magnitude of this source. And Vi is between non and INV. So those 2 terminals also listed here. Then the gain A is specified here. 1 into 10 raised to 5 is written as 1E5. Then end the subcircuit file, dot end S. Okay, now you can write the complete circuit description. So star op amp is the first line, comment line. Then VA is between 1 and 0. Between 1 and 0, VA, sine of 0, 1, 1K is the description for this voltage source. Then between 1 and 2, R1, and the value is 5K. Between 2 and 3, there is RF, and value is 50K. Then the subcircuit for this op amp is denoted by X, symbol X. Whenever you are writing a subcircuit using a subcircuit model, the name should start with X. So X1 is the subcircuit model, and we have to list the node numbers in the order defined in the subcircuit file. In the subcircuit file, we used the order non, INV, INV, common, and output. If you check the previous page, you can see we used this order: non, INV, common, and output. So the same can be used here. Non-inverting terminal is connected to 0, then inverting terminal is connected to node 2, and this common terminal is actually grounded, so that is also 0. Then output terminal is actually connected to pin number 3, so that is 3. Then name of the subcircuit, that is op amp. Then define the subcircuit file, dot subcircuit and dot end. This portion I already written in the previous page, so that can be copied here. Then you can do transient analysis for 5 milliseconds and enter the file dot end. Let us run this in LTSpace. So I have already written this in example 11. So let us open that. So here you can see first line is a comment line. Then VG is between 1 and 0. It is a sine wave source. R1 is between 1 and 2, 5 kilo ohm. R2 is between 2 and 3, 50 kilo ohm. X1 is the subcircuit model of op amp. X1, and the order of the nodes are given. Then the name of the subcircuit op amp. Then subcircuit definition. It is ending with the dot ends command. Then dot transient 5 milliseconds. So let us save and run this file. Right click and plot the input voltage waveform first. V1 is the input voltage waveform. So you can see 1 volt amplitude and 1 millisecond time period or 1 kilohertz frequency. Then let us plot the output. What is the expected output? RF is 50 kilo ohm and R1 is 5 kilo ohm. So gain of the op amp is minus RF by R1, minus 50 by 5, minus 10 is the gain. So we expect a 10 volt peak in the output with a 180 degree phase shift. So let us check the node 3 voltage or output voltage. So you can see here that there is a 180 degree phase shift and the output voltage peak is around 10 volt. Okay, that is how we can use subcircuit model in LTSpace. Thank you.